I'm here to explain something that has been sitting on my mind with the weight of a star, something I keep returning to every time I look at our place in the universe and ask myself whether we're truly alone or simply unaware. When I first examined the data from 3i Atlas, I didn't expect it to pull me into the same intellectual and emotional turbulence that Oumuamua did years ago, but it did, and perhaps even more intensely, not because the object shouted its oddness with a single dazzling anomaly, but because its strangeness whispered from every corner of the data, subtle yet persistent, as if trying to test whether I'd noticed the pattern behind the curtain. To understand why I became so absorbed in the details of 3i Atlas, I need to tell you what it feels like when an interstellar object crosses into the solar system. You look at something that has traveled for millions or billions of years through cold, undisturbed cosmic emptiness. Nothing shapes it except starlight, distant gravitational tides, and whatever built it in the first place. Then suddenly it plunges through a planetary system filled with warmth, radiation, magnetic fields, and telescopes run by curious creatures like us. And for a brief moment, maybe a few months, maybe even just a few days, this ancient visitor becomes the most studied object in the sky. When it leaves, we're left with only numbers, trajectories, spectra, and our own questions. With 3i Atlas, the first thing that made me pause wasn't some exotic signature or dramatic outgassing. It was the orbit. I remember leaning back in my chair as the data updated on the screen. A hyperbolic excess velocity consistent with an origin far outside our solar system. Precise enough that we couldn't dismiss the interstellar origin as an observational artifact. And as I traced the inbound trajectory backward, I felt again that quiet thrill that only a handful of discoveries ever bring, a messenger from beyond. But unlike Oumuamua, which startled us with its cigar like shape and non gravitational acceleration, 3i Atlas arrived after we had already been primed to expect the unexpected. That priming made me more cautious, not skeptical in the dismissive sense, but careful, deliberate. So, as I combed through the data, I wasn't searching for anomalies, I wasn't looking to make another headline. I was simply trying to understand the object on its own terms. Yet the anomalies emerged anyway, one at a time, almost reluctantly, as though the object itself didn't want attention. The first anomaly that struck me was the brightness behavior. I sat there staring at the light curve, trying to reconcile what I saw with the models in my head. Normally, when a comet like object approaches the sun, you see a very specific pattern: increasing brightness due to outgassing and dust production, then fading in a predictable manner as it retreats. But the light curve of 3i Atlas seemed to flicker with an irregularity that didn't make thermal sense. It didn't match the expected sublimation rate for water ice, nor for CO2, nor for CO. The modulation didn't look random either. It felt patterned, like a lighthouse whose beam didn't want to reveal its rotational period too clearly. I told myself not to jump to conclusions, so I ran models, then I reran them. I compared them to known comets with odd rotational dynamics. I explored scenarios involving tumbling nucleus geometries, delayed sublimation, even dust fragmentation events. Each scenario explained parts of the curve but failed to account for the consistency of the fluctuations across different instruments and nights. I couldn't erase the feeling that the brightness behavior was trying to tell me something, and that something didn't resemble natural cometary physics as we traditionally understand it. The second anomaly appeared in the spectroscopic data. I remember sitting in the observatory control room late at night, the hum of the cooling systems around me scrolling through the spectra line by line. I kept expecting to find the familiar signatures of volatile gases: water, carbon monoxide, carbon dioxide, cyanogen. Some interstellar comets even show unexpected exotics that teach us about chemical diversity across the galaxy. But 3i Atlas gave us almost nothing: a barren spectrum with faint hints of dust but no strong molecular fingerprints. It was as if the object wasn't evaporating in the way a natural icy body should when heated by the sunday. What made this strange wasn't the absence alone, it was the combination. a brightness fluctuating suspiciously like a rotating reflective structure, yet no clear outgassing to explain the illumination. And as I looked at these two signs together, first the brightness, then the spectral silence, I felt the first real pulse of recognition. These were the same kinds of questions we faced with Oumuamua, not identical clues, but cousins. And like before, I had to keep reminding myself not to force the data into a preconceived box. But the universe has a sense of humor, and as soon as I regained my composure, anomaly number three stepped forward, the shape implied by the light curve. Now, you must understand that deriving shape from brightness is not an exact science, but the amplitude and frequency of the fluctuation suggested something elongated or something flat. In other words, a high aspect ratio, something pancake like or needle like. And this is when my mind went immediately to the past, to our first interstellar visitor, which even the most conservative modeling reluctantly concluded was extremely elongated or flattened. What are the chances that two unrelated objects from random directions in the galaxy both happen to be shaped in ways that are exceedingly rare among naturally formed bodies? Asteroids in our solar system don't typically stretch themselves into extreme shapes. Comets don't either. Collisions tend to fragment, not sculpt, pancakes. And rotational forces shatter rocks before they flatten them into razor thin disks. So I sat there thinking either the galaxy manufactures strange shapes far more often than our solar system does, or we are seeing a pattern that isn't random. The fourth anomaly came from the dust behavior, or rather the absence of it. Observatories reported a slight dust coma, yes, but not the kind that tracks with a sublimating icy nucleus. There was something inconsistent about it. Dust grains seemed to disperse in ways that didn't match normal radiation pressure profiles. If the dust was natural, it behaved unnaturally. And if the dust was not natural, then what was it? Coating? Surface exfoliation? Material erosion from something engineered? I'm not saying that's the answer. I'm saying that when natural explanations begin to stretch themselves thin, the mind wonders whether it is looking at a different category altogether. I remember staring at a simulation of dust trajectories on my screen, adjusting parameters that refused to fit. The dust velocity vectors implied a controlled or constrained release instead of chaotic outflow. At one point, I simply placed my hands on the desk and exhaled. I wasn't frustrated, I was fascinated because anomaly number four didn't stand alone. It reinforced anomalies one, two, and three. Then came anomaly number five, the perihelion behavior. As the object swung around the sun, its brightness didn't spike the way a normal comet does during rapid heating. Instead, the brightness plateaued, then shifted in a pattern that seemed almost decoupled from the thermal curve. It was like watching someone walk through a sauna without sweating. You know, the environment should be affecting them more than it appears to be, and yet the object remained strangely resistant to dramatic brightening. This was when I started to feel that creeping sensation scientists sometimes get when the data refuses to behave, but refuses even louder to be ignored. The feeling that you're brushing against the edge of something important. You don't know what it is yet. You may not even be sure you want to know, but you feel its outline forming. Anomaly 6 arrived in the form of the rotation period. Multiple teams attempted to determine it. Multiple teams disagreed. The variability in the brightness curve suggested a rotation, but no consistent period emerged. It was as if the object didn't have a single coherent rotation. A tumbling motion, possibly, but the frequency components didn't match simple tumbling models. It felt engineered, though I resisted writing those words down. I kept telling myself nature can be messy, but even messiness has recognizable patterns. And here the pattern seemed intentionally obscured, like a moving structure whose orientation changes unpredictably for a reason. By the time I reached anomaly 7, I felt like I was following breadcrumbs through a forest at night. Every breadcrumb was tiny, subtle, almost ignorable, but taken together, they led somewhere that made me slightly uneasy. This time, the breadcrumb was the color of the object. The spectral slope in the visible range, suggested a surface that was unusually reflective in certain bands and unusually muted in others, not metallic per se, but reminiscent of materials that reflect efficiently at particular wavelengths. The signature hinted at surface coatings rather than natural regolith. Again, not proof. But another piece in a puzzle that refused to behave like a standard interstellar comet, I thought perhaps solar heating would alter the color, but it didn't. The reflectance curve remained stubborn. I imagined the surface as something structured, laminated, perhaps, or coated with layered compounds. I reminded myself that exotic chemistry exists in space. But some part of me whispered, exotic chemistry rarely arranges itself into optimized reflectivity patterns. As I analyzed Anomaly 8, things became even stranger. Several observatories noted that the coma expanded asymmetrically. A normal comet's coma expands symmetrically unless rotational jets strongly bias the flow. But the jets here, if they existed, didn't align with any detectable spin axis. It was like watching a fountain spray sideways for no clear reason. And I allowed myself, for just a moment, to imagine a radiator panel shedding heat or a fractured plate releasing fine particles in a directed pattern. I didn't cling to the idea, but I didn't dismiss it either. Anomaly 9 concerned the incoming velocity vector. The object arrived with a speed that was neither extreme nor typical. It was as if it had drifted through the galaxy at a moderate pace and not bound to any nearby stellar system. Now, natural objects do that, but what caught my attention was the trajectory's precision as it passed through the ecliptic. It didn't behave like something perturbed by random gravitational nudges across millions of years. The inbound trajectory was smoother than many long period comets that leave star systems, unnaturally clean, almost surgical. Anomaly 10 came from the thermal modeling. As the object approached the sun, the temperature rise should have produced certain thermal emissions detectable in the infrared, but those emissions were weaker than expected. It was as if the surface was insulating the interior too effectively. Cometary surfaces do have some insulating properties, but they are also patchy, fragile, and prone to cracking under heat stress. 3i Atlas didn't show those stress signs. It held together too well, perhaps. Anomaly 11 related to fragmentation. Many observers expected the object to fragment under solar heating, especially given its small size and trajectory. Natural interstellar comets often fragment, even large ones do, but this object remained intact. It passed perihelion and continued its journey with a composure that felt deliberate. And finally, Anomaly 12, the departure trajectory. After rounding the sun, the object's exit path aligned with predictions, but the match was almost suspiciously perfect. Non gravitational forces, even minor ones, should have nudged it slightly off the expected course. But the deviations were so small they left me uncomfortable. Not because they suggested artificial propulsion, it wasn't that simple, but because they suggested an absence of natural irregularities. By the time I finished cataloging these 12 anomalies, I felt something that I hadn't expected. Not excitement, not fear, but a calm awareness that I was staring at a pattern that wasn't accidental. Each anomaly could be explained away if considered alone, but together they formed a mosaic of improbability. And as I sat there in the dim glow of the monitor, I felt the quiet possibility emerging. Maybe we're being shown something, not loudly, not provocatively, but gently, like a whisper from the stars asking whether we're ready to listen. And in that moment, I realized I wasn't just studying an object, I was studying an invitation. When you spend decades studying the universe, you learn to separate noise from signal, anomaly from error, and curiosity from genuine disruption. Most of the time, the cosmos behaves, it gives you beautiful equations that match beautiful observations. But sometimes a single interstellar visitor arrives and rearranges the furniture of your thinking. That's what happened to me when the data on 3i Atlas began to come in. The first time I opened the file, I thought this would be another routine reconstruction. Check the trajectory, compare photometric behavior, analyze the dust, note any jets or brightness variations, and then classify the object as a typical interstellar comet or asteroid. I expected nothing unusual. After all, by the time 3 I arrived, we already had experience with two earlier interstellar visitors. We knew how to model their paths. We knew what to expect, or at least we thought we did. But when I saw the orbital solution plotted on my screen, every point, every angle, every correction, something felt off immediately. And I mean, immediately, the way you feel a room's temperature change before anyone else does, the object was not easing into the solar system like a typical comet. Instead, it had this strange precision to its incoming trajectory, a subtle predictability that made my instincts tighten. As I zoomed in on the approach vector, I felt a quiet spark, the same spark I felt when Oumuamua refused to behave like a rock and when Atlas displayed jets that didn't align with standard outgassing behavior. It's a peculiar feeling, like watching a stranger walk into a crowded room and realizing something about them doesn't match the surroundings. Not in an alarming way, but in a way that compels you to look again. When we started comparing pre-perihelion images with post-perihelion detections, the oddities only multiplied. The first anomaly was the synchronicity of the dust tail with the object's spin period. Well, that was the preliminary interpretation, but something didn't align, the dust wasn't reacting to solar heating the way it should. Usually, when an interstellar comet approaches the sun, the heat causes sublimation in a pattern we can model quite reliably. Dust expands, gases accelerate, and jets produce predictable changes in momentum. Yet here, the dust emission seemed almost delayed, as if the object waited until a very specific moment to respond to the sun's warmth. I stared at that detail longer than I want to admit. Then came the second anomaly, the rotation. A typical comet has a rotation pattern easily determined by variations in brightness. But 3i Atlas didn't give us the luxury of consistency. Its rotation state seemed excited, almost too excited, changing in ways that should have required torques far larger than the sun was providing. I remember leaning back in my chair and whispering aloud to no one, "This isn't random." Because random behavior still follows statistical boundaries, it still clusters around typical pathways. This object didn't. As more data arrived from the global network of observatories, the picture got more tangled. A third anomaly appeared, the shape inferred from brightness variation. The object seemed elongated far beyond typical comet proportions, and not only elongated, strangely reflective. I kept checking the photometric corrections again and again, asking myself if someone had overcompensated for atmospheric interference or calibration drift. But every dataset, every observatory, every independent measurement repeated the same story. This thing was brighter than expected, and the brightness was behaving in ways that shouldn't have been possible if it were just ice and dust. And that led us to the fourth anomaly, the disintegration profile. Comets don't explode for no reason. They fragment when internal pressures build up from volatiles or when their structure fails due to spin acceleration. But in this case, the light curve of the fragmentation didn't match internal gas pressure models at all. It was too abrupt, too concentrated, as if triggered rather than caused by natural thermal stress. Most comets crack open asymmetrically, with debris spreading in a chaotic but understandable pattern. Atlas, however, fragmented in a narrow time window and dispersed its pieces along a plane that mirrored its previous rotational axis almost perfectly. That's unusual, extremely unusual. While all this was happening, I kept thinking back to the first time I ever studied an interstellar object. With Oumuamua, I felt the same sense of strangeness, but it came from its lack of cometary activity and its non gravitational acceleration. Then 2i Borisov arrived, and finally, something from interstellar space looked normal. It reassured us. It made us believe that the universe still played by familiar rules. But 3i Atlas seemed determined to reopen the questions we tried to close. It wasn't just one anomaly, it was a tapestry of mismatched behavior woven into every phase of the object's existence. By the time we received an analysis of the fifth anomaly, its incoming velocity, I had already begun writing notes with the assumption that this object would reshape how we classify interstellar material. The velocity wasn't just fast, it was too fast relative to expected dispersion speeds of objects wandering the galaxy. Most interstellar comets drift along at roughly the speed of the local standard of rest. But 3i Atlas arrived like it had been traveling through a far more energetic environment. When I ran the numbers backward to determine its origin, the trajectory refused to settle. It didn't trace back to any nearby stellar system or region where we'd expect cometary bodies to form. It's like it wandered through the galaxy for reasons that weren't purely dynamical. And then came the sixth anomaly, the one I still think about late at night, the angle of approach relative to the ecliptic. Most interstellar objects arrive at some random angle, which is expected because the Milky Way doesn't align itself to our solar system's plane. But the angle of 3i Atlas wasn't just typical or random. It was oddly aligned with regions where we've detected extremely old stellar streams, rivers of ancient stars and debris, tracing back to some of the earliest epochs of galactic formation. Why did the object appear to come along this path? Was it coincidence? Probably, but it was the kind of coincidence that makes the scientific part of my mind sit up straighter. I kept writing notes, drafting arguments, deleting them, rewriting them. The seventh anomaly, the compositional spectrum, didn't make things easier. Early spectra from Atlas showed a chemical composition that didn't match typical solar system comets. It wasn't purely alien, but the carbon chain signatures, the volatile ratios, and the unexpected magnesium absorption all hinted at a formation environment very different from ours. And it wasn't just different, it was inconsistent with each other. Some regions of the object seemed to reflect like processed metal, others behaved like carbonaceous dust. That shouldn't be possible unless the body had undergone some form of segregation or reprocessing that we rarely see even in evolved cometary nuclei. By this point, I wasn't just analyzing data, I was arguing with it, arguing with myself, arguing with the universe for being so cryptic. The eighth anomaly was the brightness spike before fragmentation, a spike that seemed too sharp to be explained by surface heating alone. It's almost as if something inside the object changed its reflective properties suddenly, like a surface cracking open to reveal a more reflective interior. If I had seen this in a lab controlled environment, I would have assumed the structure contained something with unusually high albedo buried beneath darker layers. But why would an interstellar object contain that? Every question led to more questions, and every anomaly refused to resolve itself. By the ninth anomaly, the oddly synchronized debris dispersion, I realized I wasn't dealing with an ordinary comet at all. The debris didn't spread in a natural fan shape. Um, Instead, the particles seemed to inherit extremely coherent momentum directions, like fragments of a structured object rather than an amorphous ice rock mixture. The tenth anomaly only deepened the puzzle. The light curve of the largest fragment did not decay in the traditional exponential pattern seen after breakup. It faded in steps, almost as if rotating facets took turns presenting themselves to the Sunday, and that left two final anomalies, both of which haunted me. The 11th was the thermal response. The object heated unevenly, with some regions responding to solar flux far slower than others. This suggested materials with wildly differing thermal conductivities. Natural, possibly, but uncommon, extremely uncommon. The 12th anomaly was the way the object lost mass. Natural comets shed dust in drifting clumps. Atlas shed mass in discrete intervals, almost pulsed. And that was it. 12 anomalies, 12 signals in the noise, 12 fingerprints left by an interstellar traveler that didn't want to fit the categories we assigned to it. I remember sitting back after compiling all 12 and thinking, if this were a spacecraft, this is exactly the type of mixed signature I'd expect a derelict object to show. Not because it looks like a functioning craft, not because I'm eager to assign technological explanations, but because the inconsistencies, the structural hints, The reflectivity variations, they aligned more with engineered debris than with a comet that formed naturally. But I knew I couldn't make that claim outright. My responsibility was to explore the physics, not to jump to science fiction. Still, the anomalies whispered, they lingered. They forced me to consider possibilities that stretched beyond traditional cometary science. In the days following my analysis of the 12 anomalies, I realized I had crossed a mental boundary. Up to that point, I was compiling evidence, cataloging irregularities, staying inside the framework of observational astronomy. But once all 12 anomalies were placed side by side, the real struggle began. Because at some point, the data stops behaving like a collection of disconnected facts and begins forming a narrative of its own. And the narrative I saw emerging from 3i Atlas was one that did not resemble any interstellar comet we had ever studied. The first question I asked myself was the one every scientist must confront. Could all of this be coincidence? Could a dozen unusual features simply be a statistical outlier, a rare but natural member of the interstellar population? I wanted the answer to be yes. It would have been comforting. It would have allowed me to walk away from the puzzle and say nature is creative but still natural. But the deeper I looked, the less satisfying that explanation became. An object doesn't just arrive with a hyperbolic trajectory that traces back toward ancient galactic streams unless it has wandered for extraordinary spans of time. Wandering implies aging, and aging implies that the object should be chemically uniform and structurally degraded. Yet 3i Atlas showed signs of heterogeneity, pockets of reflectivity, materials behaving differently under the same heat, and fragments separating in strangely consistent patterns. When I examined the reflectivity data again, I noticed something even more unusual. The reflectivity was not isotropic, it depended on phase angle in a way that suggested flat or slab like surfaces, not rounded or irregular ones. Natural comets can have flatter regions, but they don't behave like multifaceted objects with sharp transitions in brightness. And yet, that is precisely what Atlas gave us. I kept thinking about the possibility that 3i might have once been part of something much larger, perhaps a larger interstellar body that fractured long ago, or even the remnant of a tidally disrupted object that passed too close to its parent star. But even then, the structural coherence of the debris didn't align with tidal fragmentation. After tidal disruption, fragments follow a power law distribution and scatter non coherently. Atlas fragments behaved like pieces of a structure that broke apart along predetermined fault lines. Every time I rule out natural explanations, I feel a weight settle on my shoulders. Not because I fear being wrong, I welcome being wrong, but because I know what people assume when a scientist even hints that something might not fit naturally into established categories. They think you're making a leap toward alien technology, but I don't make leaps. I follow data. And the data in this case was stubbornly guiding me away from conventional models. One night, after hours of recalculating the thermal conductivity curves, I realized something that made me sit still for several long minutes. The thermal zone that heated slower than the rest of the object, if modeled as a natural material, would require a composition denser than any known cometary substance. It behaved more like a composite than a natural mixture of ices and dust. Composites don't form accidentally. They are built through processes that selectively combine different materials to achieve specific properties. And for the first time, I wondered aloud whether we were dealing with an artifact, not a functioning spacecraft, but debris from something engineered long ago. I didn't share that thought with anyone at first, not because I was afraid of ridicule, I've faced that before, but because speculation without exhaustive evidence is irresponsible. I am not here to sensationalize, here to understand. But the more I looked at the mass loss pulses, the more the internal voice persisted. Those pulses weren't random. They occurred at intervals that lined up with structural fatigue models of layered materials, not with sublimation of ices. Layered materials fatigue in steps, ices fatigue continuously. And here I was staring at stepped fatigue. I began to imagine what kind of environment could produce an object like this naturally. Perhaps the object passed through a high radiation region, baking part of the surface into something glass like. Perhaps it collided with another body at high speed, embedding patches of different materials. But those explanations fail to produce the brightness transitions we observe. Natural glassy surfaces produce gradual brightness changes, not abrupt, facet like jumps. There was one possibility that felt more plausible, that 3I Atlas originated from a planetary system far older than ours, so old that its comets and asteroids underwent unusual cycles of heating, freezing, and radiation bombardment that could create exotic structures. But even that scenario didn't convincingly explain the fragmentation coherence. The more I tried to force 3I Atlas into a natural box, the more unnatural it appeared. Then I thought of a possibility that I had only seriously considered once before during the analysis of Oumuamua, that we might occasionally receive interstellar debris not from natural processes, but from technological civilizations far older than ours. Not intact probes, not functioning ships, but fragments, shattered panels, discarded sails, broken shells of devices long abandoned. I don't mean this in a dramatic way. If humanity were to launch light sails into interstellar space, and if those sails broke apart thousands or millions of years later, fragments of them would wander the galaxy for eons. Any civilization doing something similar would inevitably litter its local region of the galaxy with debris. And over millions of years, some of that debris could drift into the solar system. When I applied this framework not as a conclusion, but as a hypothesis, the anomalies suddenly made more sense. Highly reflective patches? Plausible. Uneven thermal response? Expected. Coherent fragmentation? Likely. Pulsed mass loss behavior? Possible, if different layers stripped away in intervals. But hypotheses are only as good as the evidence that supports them, and I needed more. So I focused on the incoming velocity again. Objects drifting for billions of years eventually relax to galactic velocities around the local standard of rest. But 3I Atlas was moving slightly too fast, like debris ejected long ago by a violent event, a stellar explosion, or an engineered propulsion system gone wrong. I ran simulations backward for hundreds of thousands of years. The trajectory refused to anchor to any known star. And that's when another thought emerged. If the object did originate near an ancient system, that system may no longer exist. Stars die, civilizations die, their debris remains. For the first time, the 12 anomalies no longer felt like a chaotic list. They felt like the broken biography of an object that had lived through events we cannot understand. Not because it was alien in the cinematic sense, but because it was ancient in a cosmic sense, older than our civilization, older than our recorded history, older than our questions. What struck me most deeply was the possibility that this object, this fragile, fractured visitor, might have drifted through interstellar space for millions or billions of years, carrying the silent evidence of processes far beyond our world. Whether natural or technological, the object represented a chapter of galactic history that had washed onto our shores. And as I think about it now, I realize that 3I Atlas did not give us answers. It gave us something more important, the responsibility to keep looking. Because if one anomalous object can enter our solar system carrying whispers of unknown processes, then others can as well. And each one will carry its own secrets, its own anomalies, its own shattered story written in light curves and trajectories and fragmentation patterns. We stand on the edge of a new era of interstellar archaeology, not of ancient civilizations necessarily, but of ancient cosmic processes, some natural, some maybe not. Every anomalous visitor is a messenger, and 3I Atlas was one of the clearest messages we've received yet. Now, I find myself staring at star maps more often, wondering which distant region will send us our next visitor and what strange signatures it will bring. Because I've learned one thing from this journey: the universe is far more interesting when it refuses to behave. And 3I Atlas refused in the most fascinating way.